How is everyone today? Good, okay. So we were talking about functions, and we're still talking about them. So to bring us back into what we were talking about last time, we had ended and we were talking about parity. And if we say let n, little n, be in the naturals. So let little n be in the naturals. That's kind of bright, isn't it? Maybe I can. Oh, not that one. Is that okay? Okay. So let n be in the naturals. So if n is divisible by 2, then n is called even. Which is to say, you would say its parity is even. You could say, you could ask the question, what's the parity of 14? Even. Okay. If not, so if not divisible by 2, then n is odd. Okay. So is that focused? Is that better? Okay. So if not, then it's odd. Okay, so then like you could say, well, 14 that's even, and 13 is odd. Now understand that what that means is that you can imagine it, a physical process where you're saying, well, I'm going to take some number of M&Ms. So say like you take 13 M&Ms, and then you start making groups of size 2. How many groups of size 2 can you make? 6. And after you've made those 6 groups, why are you not able to make another group? Yeah, because there's just one left over. So the fact that you go through that process and there's one left over, that's what odd means. And with 14, you'd be able to make 7 groups, and then there wouldn't be enough left to make a group, and the amount left over would be 0. So that's why 14 is even. So how about 0? Is 0 even or odd or what? It's even. It's even. So let's do a task. Okay, so I just put 0 M&Ms in front of you. Please make groups of size 2 and let me know when you're done. Okay, so now that you're done, how many are left over? 0? 2. So now, because there's 0 left over, that means that 0 is even. So 0 is even. Fine, but not every real is even. For example, we like just writing down the things that we said. We said that 14 is even. 13 is odd. And we're saying this about naturals. So I want to say that note that pi, meaning that number that starts with with 3.1415, that one, pi is neither. So if you ask the question, is pi even? The answer is no. And if you ask the question, is pi odd? The answer is no. It's not. It's not either one of those. Okay, so fine. Then last time we were talking about transformations of functions, and the place that we left off was we said something like this. We said let f be a function. And we said if it is the case that f of negative x is f of x. If f of negative x is f of x for all x, then f is even. But understand that that doesn't really have anything to do with the sense in which a number can be even. So they're not the same. So we've got parity of naturals, and we've got parity of functions. So a natural can be even or not, and a function can be even or not. So let's try and remember, why this definition is reasonable and what it means. So as an aside, so recall that last time we said, well, if you take a function and graph it, y is f of x, and then you mess with it and you say that I'm going to leave the y as it is, but what I'm going to do is I'm going to negate the x, like that. So when you do that, there's a name for what you've done. So you didn't do anything to the y's, so we didn't do a vertical thing, but we did do something to the x's. We negated all the x's. So we must have done a horizontal thing. What horizontal thing did we do? What's the name of that? Starts with a R. That one. So that's a reflection. So this is a horizontal reflection. So that's a horizontal reflection. So what I want you to see, what this statement is saying, what that statement is saying, is that the left-hand side is a horizontal reflection. So the question that you're asking, you're saying if a horizontal reflection is the same as the original, if a horizontal reflection is the same as the original, then you're going to call that function even. So that's the meaning of that. So the reason to use the word even is in the end because of the following. Example, you could say, well, I could ask, here's a plot that you're supposed to have memorized, the plot of the standard parabola. So if I plot the standard parabola, it looks like this. Now, it's not usually my style to draw arrows on both sides, but I don't want you to get hung up on some symmetry thing. So now imagine that I grab the vertical axis like that. So I grab it, pick it up, and then turn it over like I'm turning a pancake, and then put it back down. So pick it up, turn it over, put it back down. Then what would the red look like? Same. And so what I want you to see is that this, the transformation is that we changed x to negative x. So we changed x to negative x and left the y's alone. Now, does that algebraically simplify? How does that simplify? Negative x all squared. Just x squared, right? Because the negative squares away. So this is y is x squared. So what I want you to observe is that this picture is and the algebra. So the picture and the algebra, it's saying that the horizontal reflection is the same as the original. That's what it means to be even. an even function. So, notice that that equation is the same as that equation. That picture is the same as that picture. And that works. That negative gets canceled in the end because 2 is even. Right? It would have worked the same. The picture would be more or less the same as if instead of being y is x squared, it would have worked with y is x to 4. It would not have worked with y is x to 5, but it would have worked with y is x to 6. That would have worked. So in fact, it's going to work anytime that exponent is an even number. So that's the reason to call these functions even. Okay, so then besides being even, we've got another possibility. So now algebraically it reads, if f of negative x is, so right here, what I've written so far, that's exactly the same as the first one, right? So far it's exactly the same. So there's no sense in writing the same thing twice. So I need to make some difference here. So now instead of the right-hand side being that, now the right-hand side is going to be this. So that negative is what is new for all x. Then f is odd. Okay, so let's understand the meaning of that, why that definition should make sense, and what it means. So recall that, so this one, what we did is we changed x to negative x. That's what we did, x to negative x. So now I'm going to do the same thing, but with the y's, which is to say that I'm going to say that we take y as f of x, and we make the transformation where the y becomes a negative y. So if the transformation x to negative x is a horizontal reflection, then the transformation y to negative y is a what? It's a vertical transformation. In a vertical reflection in particular. Vertical reflection. But notice that for this particular one, because y is all by itself, it's not inside of a function, right? Because y is all by itself, you can actually solve for y again. So what do you get if you solve for y? Uh-huh. So what I want you to see is that this equation, what that's saying, it's saying something. So this is this is saying that we'll negate the input, we'll negate the horizontal coordinate. So this is a horizontal reflection. That's what this one is. Now up here, there's no negative anywhere, so that's just the original thing. But here, there's a negative on the outside, so that means that we're negating the output. Well, that's this. So horizontal reflection is the same as what? As a vertical reflection. So to be odd, what that's saying is that a horizontal reflection should be the same as a vertical reflection. They should be the same thing. Okay. So as an example, now I'll need 3 of them. So in the middle here, I'll say y is x cubed. And x cubed, y is x cubed is something that you're expected to know. It's plot. So how does it look? Yeah, it kind of like an S. It'll be pretty much just like a parabola, except someone took the left arm and twisted it down. So it kind of looks like this. like that. And so, fine. To the so this is the original. So now going this way, I'll say that here we're going to do a horizontal reflection. Horizontal reflection. So I'll do it like this. So if this part down here, so ignoring the top part for just a moment, if just this part down here horizontally reflected, do you see that if this were a mirror, you know, what would that one see over there? It would look like this, right? Just the bottom part. Okay, and then now ignoring the bottom part and just looking at the top part, if this part was horizontally reflected, you know, and this was a mirror, and the red part was looking at the mirror, what would it see on the other side? You would see this. So something that looks like that. So now, are these two the same? They're not the same, right? In the same kind of sense that are my left and right hands shaped the same? They're not, right? Because this one has my thumb going that way, right? And this other one has that thumb going that way. Now they're the same if I do that, but that doesn't count because that's a reflection, right? So what I want you to see is that your hands are reflections of each other. You can, if there was a mirror right here, then that's what you see. Or if you were literally looking in a mirror and holding your hand up, your right hand, then the person in the mirror would be holding up their left hand. So, you know, you could say like left hand, right hand. They're not the same. Okay. You know, you can't pick this one up and put it on top of that one. Okay, fine. Going this way, let's do a vertical reflection. So now instead of reflecting left-right, we're going to reflect up-down. So I'll just look at that part. You know, since that's on the bottom, I'll reflect it to the top, imagining that to be a mirror. And if that, you know, if this red part, we're looking at that, and that was a mirror, and it reflected up, what would it look like? Well, it would look like this. Right, just the bottom part. It will go up. Okay, now ignoring the bottom part and looking at the top part, if this one reflected vertically, because it's above that, it would, you know, go down. And if this was reflected down, how would it look? Well, it would look like this. So now, well, because that's the original and that's the horizontal reflection, and those aren't the same, that means that what we're looking at isn't even. But because we have both of them up here, notice that we've got the vertical reflection and the horizontal reflection. Are those the same? They are the same. So what's the case about this? It must be odd, right? That's what odd means. So notice that the exponent there is 3, which is odd, where integers are concerned. So there's that. Now, what is the transformation that you do to the variables algebraically for a horizontal reflection? So what do you do? It is x becomes negative x, right? So taking this equation and doing that, we're saying that this would be y is negative x, and then cube that. Now up here we said, hey, look, the negative squares away. So does the negative cube away? No, right? In order for the negative to be squashed, there's got to be an even number of them, right? It worked with 2, but not 3. It works with 4, but not 5. Meaning that if you had 4 numbers and they were all negative and you computed their product, the result would be positive. Negative times negative would be positive, times one more negative would be negative, times the last negative would be positive again. So then simplifying this, it looks like this. Okay. Now, what is the variable? How do you play with the variables if for a vertical reflection? y becomes negative y. So that would mean that we'd say negative y is x cubed. Now, so that's the equation for this. Can you solve for y? What do you get if you solve for y? Yeah. Do you observe that that this equation that we obtained from the vertical reflection is the same as the equation that we obtained for the horizontal reflection, and that the plots are the same, and because the horizontal and vertical reflections are the same, then this is odd. Okay. Not to stress it too hard. So one example of this, and then we'll move on. I could say something like let h of x be equal to 5x squared, and then minus 7, I guess. That'd be nice. And then divided by 3x to 5 minus 4x. Okay. So the question is determine if h is even, odd, or neither. Because many functions can be neither, in the same kind of way that concerning numbers, pi is neither even nor odd. So most functions are neither one. Okay, so here's the strategy. So if you look at the previous page where we're saying what these things mean, notice that the question is that is one of those two equations true? So notice that both of them are saying, well, negate the input. So that one is saying negate the input, and that one is saying negate the input. The first one is saying that, well, if it's the case that negating the input is the same as doing nothing, if it's the same as the original, then it's even. And if negating the input is the same as negating the output, then it must be odd. So in either case, we need to negate the input and then check. Is it that one, or is it that one, or is it neither one of those? So what we'll do is we'll find / simplify h of negative x. And then once we've done that, we'll check is it equal to just regular old h of x, or is it equal to negative h of x? So if yes to the first question, then it's even. If yes to that question, then it's odd. If no to both questions, then it's neither one of these. Okay. So h of negative x. So the strategy here is I'll look at the formula for h, and everywhere that I see an x, I'm just going to leave an open set of parentheses. Because I'm substituting stuff in. So all those open spots, that's where I need to write stuff. Okay, so what is it that I need to write in there? Negative x. Okay, so I do that. Oh, not that one. I wanted to leave that one. Negative x, negative x, negative x. All right? So now we want to simplify this as much as possible. So in the numerator, notice that we're squaring the negative x. So how does that simplify? Just regular x squared, right? The square squashes the negative there. So that the numerator The numerator becomes what? 5x squared minus 7. All right. I can see that I'm saying subtract 4 times negative x. So that negative can come out and say I'm actually adding what? I'm actually adding 4x, right? That's getting that negative out, and then it's canceling with that one. And then how about the negative x to exponent 5? How does that simplify? Right. Well, I'll do it like this. I'll say 3 multiplied by negative x to 5. So that's one small step behind what you rightly said. So the 5 doesn't squash the negative because there's 5 of them, and then they pair up in pairs and become positives, but there's 1 left over. So then simplifying this, all right. So we've made some simplifications, and now I'm going to ask, is that exactly the same as h? Is it kind of similar to h? Seems kind of similar, right? The numerators are the same. Are the denominators the same? Not exactly, right? So notice that that's positive 3, that coefficient, and that coefficient is negative 4. And these are the opposite, right? That one's negative 3 and positive 4. Now maybe we could factor out a negative like this. So my question is that if in the denominator I factor out a negative, what do I need to write in there? All right, so 3x to 5 minus 4x. And then, that negative can be factored all the way out to the front, because remember that negation is multiplication by negative 1, and division by negative 1 is the same as multiplication by negative 1. So in fact, we could say that this is negative, and then this. So we want to look at this one. What if we factor a negative out? The reason why we want to look at that one, because remember, we're asking ourselves, is it that one? Is it that one? Well, how about that thing in round parentheses? What is that? Yeah, that's h, isn't it? So what this is saying is that this is equal to negative h of x. So as a result, we're saying that. We're saying that, hey, if you negate the inputs, that's the same as negating the outputs. Or, if you perform a horizontal reflection, that's the same as performing a vertical reflection. So what's the conclusion about h? So it's odd. So h is odd. Now here's something interesting. So a couple comments. So now I purposefully was bending a little bit your notions that you might have about parity. So naturals have parity. So they're either even or odd. All of them. So like 7 is odd, but 70 is even. Real numbers don't necessarily have parity. So like 7 is a real number and it's odd, but 7.4 is a real number and it's neither even nor odd. And I'm asking you about a function. So now it turns out that this function is odd, and I purposefully gave you just that term right there. So that term right there would be an even function if it were alone. And then, concerning functions, its parity would be even. And then I multiplied it by 5. Now 5, when you consider it just as a natural, 5 is odd. But what about 5x squared? Is that even or odd? Where functions are concerned. It's even, right? Even though the coefficient is odd. So I'm purposefully mixing the notions on purpose to check and make sure that they're separated for you. So an odd integer multiplied by an even function. Those are two different notions of parity. Similarly, that's an even coefficient, but that's an odd function. Okay. Any question about this? In the end, it's all just this. You negate the inputs and then check, is it that one? If no, then check that one. If no, then it's neither. All right. So now we've got a new thing. This is a fun thing. Oh no. So section 3.7, inverses. All right. So here we are talking about inverses. So we've got this thing called addition. You've heard of it. And what it is it's a way to take two numbers and add them together and get a new number. Okay. And it's exactly what you think it is. So, so here we go. So 1.1. The additive identity is blank. So the additive identity is a number, and it's a number such that adding this number is the same as doing nothing at all. So 0. So the additive identity is 0 because x plus 0 is x for all x. 1.2. The numbers x and y are called additive inverses. When x plus y is 0. Why 0? Why am I saying 0 is important here? Because it's the identity. So let me say these sentences out loud with a comical amount of stress on the words. So the additive identity is 0. And x and y are called additive inverses when you add them and you get the additive identity. Right? Okay. Trust me, I have a reason that I'm doing this. So 1.3. 1.3. Here's just a fact. I'll just state it without much comment. Is that all x have an additive inverse. So every number can be additively inverted. And then finally, we can do even better and say that the formula for the additive inverse of x is negative x. Because after all, if you do x plus negative x, what do you get? 0. So like, what's the additive inverse of 5? Negative 5. And what's the additive inverse of negative 8? Negative 8, which is 8, right? Okay. So fine. Good. Then we've got this other thing that you've heard of, multiplication. Well, so now I'm just going to basically copy and paste these sentences. almost, and make small edits. The multiplicative identity is blank. Is what? 1. And why is it 1? Right. Because 1 is the number that is, when you multiply with it, that's the same as doing nothing. Multiplying by 1 is doing nothing. Okay. 2.2. X and Y are called multiplicative inverses when what? One. Okay, so again, here comes the comically stressed sentences. So the multiplicative identity is 1. And X and Y are called multiplicative inverses when you multiply them and you get the multiplicative identity. So X and Y are additive inverses when you add them and you get the additive identity, and X and Y are multiplicative inverses when you multiply them and you get the multiplicative identity. Right? Can you hear it? And then, if there was some other operation called banana, then you'd say that X and Y are banana inverses when you banana them and you get the banana identity. So for whatever you want to replace banana with. Okay. So now the next question is that, so here for add, we said that all x's have an additive inverse. So is it the case that all x's have a multiplicative inverse? Because in the end you'd want to be able to take that equation for any x. You want to find some other y that when you multiply it, that x and the y, you get 1, right? So like, what would be the multiplicative inverse of, say, 2/3? 3/2, right? Because then you'd multiply them all the canceling and then you get 1. Okay. So do all numbers have a multiplicative inverse? So there's a single holdout. 0. Right? Because what could you multiply by 0 so that you'd get 1? Nothing. So now it's not all numbers, but rather all non-zero x have multiplicative inverse. And we can do even better, and in fact we can just say the formula. So the formula for multiplicative inverse of x is reciprocal, which is to say 1 over x. Because after all, if you do x multiplied by 1 over x, what do you get? 1, right? But you can't do that 1 over x if x is 0. Okay, fine. But really I wasn't actually interested in addition or multiplication at all. Rather, I was just interested in this structure. So now that I have the structure written on the page, now I can say what I actually intended to say. And that is that, remember on Monday we said that you can add and multiply and subtract and divide functions. You can do that. But there's this other thing you can do with functions that you can't do with numbers. What is that? Starts with C. Compose. So there's addition, multiplication, and here's the thing that I actually wanted to talk about. Composition. So again, just copy and paste. The composition identity is blank. So what's its name? ID. And notably, up here, when we're talking about the additive identity, we're talking about the kind of things that we're talking about as numbers. So the additive identity is a number. And when we're talking about multiplication, the kind of things that we're talking about are numbers. So the multiplicative identity is a number. But when we're talking about when we're talking about composition, the kind of things that we're talking about is functions. So what kind of thing is the identity? A function, right? That's what it is. Remember that its formula is ID of x is what? We talked about it on Monday. Just x. So it's the function that when you give it an input, the output is the exact same thing. So you put in a 5, out comes a 5. You put in a giraffe, out comes a giraffe. So nothing changes. And it is the case that if you compose f, any f, with the identity, you just get f. And if you do it in the other order, you still just get f. Now we have to write it down in both ways because composition doesn't commute in the same kind of way that pants and underwear don't commute. But addition commutes. So we only have to write it one way for add. And multiplication commutes, so we only have to write it one way for multiply. We don't have to write also yx. But for composition, we've got to write it both ways. Good? So now here's where you have to sort of pay attention. So now we've got two functions. F and G are called composition inverses when, well, when what? Sorry? What do you mean when they equal ID? Yeah, because you might be on it. You might be on it, but you didn't quite say the right thing. So again, two numbers are additive inverses when you add them and you get the additive identity. You get the compositional identity. So when you compose them and you get the compositional identity. But it has to work in both orders. And G composed with F is ID. So both orders. Okay? Which is to say that if you do G first and then follow that up with F, that's the same as having done nothing. And if you do F first and follow that up with G, that's the same as having done nothing. All right? So 3.3. So looking up here, this sentence, for add and multiply, add is saying that everything has an additive inverse. Multiply is saying that almost all the things have a multiplicative inverse, all the things except 0. And now the question is that do all functions have a compositional inverse? And the answer is going to be no. Because to run a function in the reverse direction is to be able to look at the input, look at the output, and say what must have been the input. So, for example, with the squaring function, if you witness a 64 come out, if 64 is the output, do you know for sure what was input? No, there's more than one choice. What's one of the things that could have been input if the output is 64 for the squaring function? 8. 8 could have been the input. Is that the only input? Could have been -8, right? So if you witness a 64 come out, you don't know what was input. So how do you know for sure? What's the name of that thing when for every output you know what the input was? It's a I word. There's two words. Which one? Injective. So now it's injective functions. Have a compositional inverse. So not all of them, only the injective ones. And finally, we're just going to say but not do anything yet. So notice that the last item here, we said for the fourth item in addition, we said the formula for additive inverse is negate. And the formula for multiplicative inverse is reciprocal. And so the formula for compositional inverse is next time. We're going to have to figure out how to do it. All right. So that's it for today. Have a nice weekend.